So real gases, we've been talking about ideal gases. Ideal gases have no attractions between gas particles, and the volume of them is so small it doesn't matter. At regular temperatures, especially at STP, real gases behave very much like ideal gases. And we can look at that by calculating the molar volume or measuring the molar volume of these different gases. So an ideal gas is 22.41 liters, and we see that these other gases are very close, and helium even nails it, it's exactly the same. Look at him. Yeah. But if we get high pressure or very low temperature, then we start to see deviations. So the finite volume of gas particles has an effect at high pressures. So we take this gas and we increase the pressure, we're decreasing the volume. These particles are getting closer and closer together, and the closer together they get, the more their size matters. Right? So if we took Wyoming and took all the people in Wyoming and started herding them together and started, trying to put them into a football stadium or something, now the size of the people matters, right? Because they're getting touchingly close. But when there's lots and lots of space, the size of the particle doesn't matter. So at high pressures, the volume becomes significant, and so we see deviation. The volume that we observe is larger than predicted by the ideal gas law. So we can look at it like this: molar volume versus pressure. Here in the red is an ideal gas, and at lower pressures, and these are not all that low, 200 atmospheres is still considered a low pressure on this chart. When we get to higher pressures, now we see that the argon has a slightly higher molar volume than an ideal gas, because at the higher pressure, the volume of the particles becomes important. 1873, van der Waals made a correction to the ideal gas law so that you can actually calculate the volume of a real gas. I told you about that. We're not going to do anything with that. At high temperatures, the pressure is nearly identical to that of an ideal gas. Here we're looking at the effect of intermolecular attractions. Because the fact is, when those gas particles bounce off of each other, sometimes there is a little bit of attraction. They're like looking at each other or sticking a little bit, right? At high temperatures, the particles are moving faster, and so they're bouncing off, and the effect of attraction is less. At low temperatures, they're moving more slowly, and now when they bump into each other, they have a chance to be attracted to this other molecule, and then when they move away, it's going to affect the pressure. You have less kinetic energy. So we can look at that here. The pressure in atmospheres as we increase the temperature of a gas. So up here at high temperatures, for 1 mole and 1 liter of gas, we see that an ideal gas and a real gas are the same pressure. And as we get to lower and lower temperatures, the ideal gas pressure is higher than the real gas, because the real gas gets slowed down a little bit by interacting with its other gas molecules, and so it doesn't hit the container as frequently, so the pressure is lower. And there's a correction to the ideal gas law for this as well. And you combine those together and you get this mess, which is known as the van der Waals equation. And the constants you'd have to look up in a table. And doesn't that make PV equals nRT look nice? Here we've got a graph of PV over RT, which is equal to N, versus pressure for an ideal, for gases, for 1 mole of a gas. So for an ideal gas, PV over RT is 1 all the way across. For real gases, sometimes it's lower and sometimes it's higher. So for helium, we see that the molar volume, we see that this line is above, and that's because the biggest factor here is that the molecular volume, because helium atoms really have almost no attraction to each other. For a larger molecule like water, there's a lot of attraction between water molecules, and so we see the curve dips down below the line. Molecular volume is, intermolecular attraction is the most important.